Hey everyone, let's dive right into this explainer. Today, we're doing something really exciting. We are going to reconstruct the absolute basics of aerospace engineering completely from first principles. We're not just going to sit here and memorize dry textbook definitions. No way. We're going to build a deep physical intuition for how massive, heavy metal machines actually manage to ride on an invisible cushion of air. To kick things off, picture this real-world paradox. How exactly do you design a machine to fly safely and efficiently through a fluid that completely changes its physical properties every few thousand feet? Think about it. The air down at sea level is thick and warm, but up at 30,000 feet, it's incredibly thin and freezing cold. If we want to really understand how airplanes work, we can't just start by looking at wings and engines. We have to start by decoding the actual invisible medium they fly through. So, here's our roadmap for today. 1. Decoding the invisible air. 2. The math of reality. 3. Anatomy of an airplane. 4. Form follows function. And finally 5. The physics of climb. All right, section 1, decoding the invisible air. Let's get right into defining our atmosphere. The master key to understanding the atmosphere is this single, incredibly elegant formula, the equation of state, P equals rho RT. But let's step away from the math for a second and look at the physical story happening here. Pressure, that P, is literally the physical force of millions of microscopic air molecules violently slamming into a surface, like the skin of an aircraft. Density, or rho, is simply how tightly packed those molecules are in a given space. And temperature, T, well, that's just a measure of the speed of their chaotic motion. These three things are mathematically locked together. It makes total sense when you visualize it. If you pack more molecules into a space, or if you make them zip around faster by heating them up, they're going to hit the surface harder, and your pressure goes up. It's truly that simple. Now, here is a massive trap that so many people fall into. Using everyday temperature scales like Celsius or Fahrenheit in these equations, you absolutely cannot do that. Why? Because you physically cannot have negative kinetic energy. If you were to plug, say, negative 10 degrees Celsius into our formula, you'd end up calculating a negative pressure, and physically that is just impossible. You need a zero anchor. That's exactly why engineers use absolute scales like Kelvin or Rankine. On those scales, zero truly means zero. It is the literal point where all molecular motion stops dead. Okay, let's move to a concept that's closely related to density, called specific volume. Mathematically, it's just the exact inverse of density, 1 over rho. But instead of thinking of it as a fraction, I want you to picture it spatially. It's the amount of physical elbow room each kilogram of air gets. Down at sea level, the air is packed super tight, so it has a low specific volume. But as a plane climbs up to, say, 35,000 feet, the air really spreads out. That specific volume increases drastically. Because of that, the plane actually has to fly faster just to scoop up enough of those spread out molecules to stay aloft. Which brings us right to section 2, the math of reality. Understanding the air is step 1, but modeling it mathematically means avoiding the biggest trap in engineering. So, here's something absolutely crucial. Unit conversion is not just some annoying math chore you do at the end of a problem. It is a strict, necessary translation of physical reality. If your units aren't perfectly consistent, your entire model completely breaks down. A really great sanity check in aerospace engineering is just looking at your final units. If your calculation for engine thrust ends up giving you a unit of volume, well, you've fundamentally misunderstood the physical reality of the system. To prevent those kinds of disasters, engineers use a foolproof trick that I like to call the unity hack. It's brilliant, really. You just find a ratio of the exact same physical thing, like 1 foot and 0.3048 meters. Since they represent the exact same physical length in the real world, their ratio is philosophically equal to 1, or unity. And since multiplying by 1 doesn't change physical reality, you can just chain these unity brackets together to systematically cross out and cancel any units you don't want. Let's actually see this in action with the F-117A stealth fighter. Say we want to convert its wing loading. We chain our unity ratios together. We're starting with kilograms force over square meters, and we need to get to pounds over square feet. We just systematically multiply by our unity ratios. Watch what happens. The meters cancel out the meters. The kilograms cancel out the kilograms, and boom, we are left perfectly with pounds per square foot. No guessing, no weird math magic, just a flawless translation of reality. Moving on to section 3, anatomy of an airplane. Now that we've got the math and our invisible medium defined, let's look at the tangible machine itself. Spatially, an airplane is built around a few core physical tasks. Right in the center, you have the fuselage. The word actually comes from French, essentially meaning spindle. And that's exactly what it is. It's the payload spindle. It holds the people, the cargo, the fuel. Sticking right out from it are the wings, which are your primary lift generators. And at the back, we have the horizontal and vertical stabilizers. Think of these exactly like the feathers on the back of an arrow. They ensure the aircraft flies straight and doesn't just tumble uncontrollably through the fluid air. But obviously, a plane needs to maneuver, right? It can't just fly straight forever. To do this, we use control surfaces. These are the hinged flaps you see on the trailing edges of the wings and the stabilizers. Ailerons make the plane roll. Elevators pitch the nose up or down. The rudder yaws the nose left or right. And the flaps, they increase total lift when you're taking off or landing. What these surfaces are actually doing in real time is dynamically warping the plane's shape to manipulate the pressure distribution of the air we talked about back in Section 1. And that brings us perfectly to Section 4, Form Follows Function. Because once you deeply understand these basic physical principles, you can start to radically rearrange them. Take a look at the Lockheed Martin F-117A stealth fighter. It looks like an alien spacecraft compared to a conventional airliner. Why? Because its primary function was not maximum aerodynamic efficiency. Its primary function was to be literally invisible to radar. Those flat, faceted panels deflect radar waves away from the source. The aerodynamics actually had to be heavily compromised just to satisfy that one specific overriding design requirement. Or compare a standard swept-back wing jet, which is designed to reduce drag when flying near the speed of sound, with a totally radical design like the X-29A. The X-29A sweeps its wings forward to get incredible maneuverability, and it places its stabilizers all the way at the front instead of the back. Aerodynamically speaking, the physical forces at play here are actively trying to twist the wings right off the plane. It was literally only when super strong composite materials were invented that this radical form became physically possible to build. Finally, let's bring everything we've learned together into Section 5, the physics of climb. How does a machine weighing tens of thousands of pounds actually ascend into the sky? It all boils down to a brutal battle of power. On one hand, you have the power available. That is the sheer raw thrust your engines generate. On the other hand, you have the power required, the energy needed strictly to overcome the aerodynamic drag of the air trying to hold you back. The magic of flight happens in the gap between those two numbers. The difference between the power you have and the power you strictly need is what we call excess power. To give you a real, visceral sense of scale here, 4,700. That is how much horsepower of excess power a standard twin-jet transport aircraft might have. And remember, that is not total power. That is just the leftover excess power available after all the drag has been fully beaten. It is a massive, almost unimaginable amount of force. And what does the plane do with all that leftover muscle? It uses it to physically punch up through gravity. Your rate of climb, literally how fast you gain altitude, is exactly proportional to your excess power divided by your weight. Here's a quick sanity check. If you load up a plane with extra cargo, increasing the weight, the bottom of that fraction gets bigger, so your overall rate of climb drops. You're using that excess horsepower to fight gravity and shove the airplane up into the ever-expanding specific volume of the higher atmosphere. We've covered a ton of ground today, right? From the microscopic behavior of gas molecules to the raw, brute force horsepower required to climb into the sky. Aerospace engineering isn't just rigid math. It is a beautiful art of continuous compromise. Airplane design is an open-ended problem. There is literally no single right way to do it. So the next time you look up and see a massive metal tube flying through an invisible ocean, ask yourself, what hidden physical compromises did engineers have to make just to keep that perfectly balanced equation in the sky? Thanks so much for joining me on this explainer, and keep your eyes on the skies.